let me quickly go over a Black-Scholes equation and how to derived. We go from the assumption of ds equal to 𝜇𝑆𝑑𝑡 𝜎𝑆dZ, where z is a Brownian motion, and this is essentially can be considered as a variation. It is the variation over time, and a drift variation, like certain level of variation of the Brownian motion, and essentially a risk, and sigma is a drift, go up and down with certain driving force. We start with a general function of a time and s, where s is a multi-dimensional vector that can be expressed as say as a stock price, where s is the stock price, can be. And we just do Taylor expansion using the Ito's correction, meaning outside of this first order, we'll expand the second order. So this line is the first order. These are the second order. And as we know from the quadratic variation and the bracket operation, we know that dt squared is equals 0, ds dt is 0, and this is not 0 when I equal to j in this term. So this go to 0, this go to 0, we're left with this, which is essentially dt from the quadratic variation. So we have this term, and this term left. Not dt. We need to expand this. Sorry, ds is not solely Brownian motion. We need to expand this. So plug in the ds equals to, in terms of dt and dz. We have after some algebra, we have this expression. Since dt squared go to 0, this go to 0, and then dz squared is dz squared is dt. We're left with this expression. Where dz is just a Brownian motion. We set the the general function as a price of the stock in the money value at time t. So we need to discount it to e to the negative rt, where r is like interest, for instance, and where g is is using the money value at the current time. So we need to ultimately interest on g, because g is the actual price. We see in our stock market, for instance. Then we'll just plug in this expression that for f into this formula, into this differential equation. We have this. since derivative of time, you have to do by part this left first the exponential and g. Since this extra term is only involved in time instead of s, thus it doesn't pass through any of these terms. Sorry, there's t missing. And tidying everything up, put RT all the way to the out of the bracket, out of the parentheses. We have this expression. If we integrate on both sides, we have this on the left side. On the right hand side, we'll just put integrate from 0 to t, where t is a maturity time for an option, for instance. Using the risk neutral measure, the discounted price expectation value of discounted price should be a martingale in the complete. Should be a martingale. Thus, is that equal to 0? Then this equal to 0. So for this equal to 0 for any event at any given time, we have to make sure that anything in the parentheses are 0. Then we're left with those two equations, equal to 0 with a boundary condition of f equal to 0, f equal to 0, f equals g equals 0, g is 0, where essentially is the price, the starting time, the price of the starting time, as a function of the price of the starting time, where the f and g are the derivative, because it's essentially it can be a derivative in the sense that it's a function of time and stock